So to continue our discussion in Chapter 3, we will now proceed to helical spring. On this part, we will be dealing with the shearing stresses and the deformations or the elongations that a helical spring is experiencing. And a helical spring is composed of closed coil of wires that are round rod with diameter D and form a helix with a mean radius R with a certain number of turns. So yung diameter na tinutukoy dito is the diameter of the rod or ng ating wire, and it is composed of a certain number of turns that forms a certain mean radius ng ating helix. So ito yung magiging mean radius ng ating coil or ng ating helical spring, and it has certain number of turns. So for this illustration, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 turns ng ating helical spring. So if we try to load a certain load sa ating helical spring, it will create deformations. And if I will cut a certain portion ng ating helical spring to identify yung mga forces that is acting upon it, we have here our P, and to be able to balance the applied load P, the exposed shaded cross section, which is this one, we have the exposed cross section, must provide the resistance that is equal to our P multiplied by the radius of the coil. And this diagram is now in equilibrium for both vertical and horizontal summation of forces. And to complete the equilibrium, we will provide a moment summation that is equal to 0. So taking a summation of moment to the exposed area or the exposed cross-section area, we have P multiplied by the radius or the mean radius of the helix. So this is a resisting couple that is created by a torsional shearing stress distributed over the cross-section that is equal to P multiplied by R. So the moment or the couple is equal to P multiplied by the R. So helical spring is experiencing two types of shearing stress. First one is the direct shearing stress. So let's say this is shearing stress 1 that is uniformly distributed over the spring section that creates the resisting load PR. So yung shearing 1 natin is equal to the force multiplied by the cross-sectional area. And the other type of shearing stress na nag-act sa ating helical spring is the torsional stress. That is let's say equal to shear 2, and the variable torsional stress is caused by a twisting couple that is represented by our torque multiplied by the radius all over J or the polar moment of inertia, and our torque is equal to the load multiplied by the mean radius of the helical spring. So the maximum shearing stress that the helical spring is experiencing will now be equal to the direct shear stress plus the torsional stress. And to simplify this equation, we will substitute the values of the direct shearing stress and the torsional shearing stress. So, magiging the maximum shearing stress would now be equal to P, and then the area is pi d squared all over 4 plus yung ating torsional stress, which is equal to P multiplied by R, and then yung R natin is equal to D all over 2 divided by the polar moment of inertia, which is pi all over 32 d raised to 4. So, further simplification, magiging T all over pi d squared all over 4 plus this one, cancel this out, magiging 3 yan, and then multiply natin, magiging 16p multiplied by the mean radius all over pi d raised to 3. And then, so we have 16 PR all over pi d cube, and then 1 plus d all over 4 multiplied by the mean radius. So this would now be our equation for the maximum shearing stress of helical spring. So ito yung gagamitin nating formula in determining the maximum shearing stress ng ating helical spring, in which the maximum shearing stress is equal to 16 multiplied by the applied load multiplied by the mean radius of the helix divided by pi, the diameter of the wire, raised to 3 multiplied by 1 plus the diameter of the wire divided by 4 multiplied by the mean radius of the helical spring. So this formula neglects the curvature of the spring and is used for light spring, where the ratio is equal to D all over 4 multiplied by R. So for heavy springs, we are considering the curvature of the spring, and it is introduced by A.M. Wall, in which he developed a formula on the ratio of the diameter of the wire with the mean radius of the helical springs. So the ratio of the mean diameter of the spring to the diameter of the wire is represented by certain constant M, or spring index, in which our M is equal to 2R multiplied by the diameter of the wire. So kaya magiging diameter all over the small letter D. So this is the ratio of the mean diameter of the spring to the diameter of the spring wire, and it is called as the spring index. And A.M. Weil formulated or made a formula in which the maximum shearing stress is equal to 16 P multiplied by R all over pi d cube multiplied by 4 times the spring index minus 1 all over 4m minus 4 plus 0.615 all over m. So this is another formula in solving the maximum shearing stress by A.M. Wall. So this formula is applicable for heavy spring and when you are considering the curvature of the spring. So for light springs where the ratio M is large, the first term in the parentheses 4m minus 1 all over 4m minus 4, or this wall factor, so ito yung tinatawag na wall factor, is approaching unity or is approaching 1. So we can rewrite the formula as this one. So this is applicable for light spring. So magiging 16 PR all over pi d cube. So, the wall factor is approaching 1 or approaching unity. So, maging 1 minus 0.5 all over m. So, this is another formula for the light spring when we are considering the curvature of the spring. So this formula is for heavy spring and this one is for light spring. As I have said earlier, that if we load a certain P sa ating helical spring, magkakaroon siya ng deformation. And the deformation now would now be equal to 64 multiplied by load, the mean radius r raised to 3 multiplied by the number of turns divided by g or the shear modulus ng ating material, d raised to 4. So ito na yung formula ng ating deformation or ng elongation ng ating helical spring. And also we have a constant or what we call a spring constant K that is equal to the ratio of the load and the elongation. So we have here P and then yung ating load 64 P r raised to 3 multiplied by n all over g d raised to 4. So canceling out P here. Yung ating spring constant now would now be equal to g d raised to 4 all over 64 r raised to 3 multiplied by n. So this is now our formula for the spring constant K. So this formula. And then our K can be determined depending on the spring or depending on the orientation of our spring. So we have here the springs in series, in which on this example we have two kinds of spring constant depending na rin sa helix or the radius of the helix. And then for the springs in series, we have also this kind of orientation. So kindly take note that springs are made of special steels and bronze that has allowable shearing stress that is ranging from 200 to 800 megapascal or 30 to 120 kilopounds per inches squared. So to further understand about helical spring, let us have our first example. For our sample problem 1, determine the maximum shearing stress and elongation in a helical steel spring that is composed of 20 turns of 20 mm diameter wire on a mean radius of 90 mm when the spring is supporting a load of 1.5 kN. Use AM wall formula and the shear modulus is equal to 83 gigapascal. So we have here 20 turns yung given natin. And then the diameter is 20 mm with a mean radius of 90 mm. And the spring is supporting a load of 1.5 kN or 1,500 Newton. And the shear modulus of elasticity is equal to 83,000 Newton per square millimeter. So we will determine the maximum shearing stress and the deformation or the elongation. So for the maximum shearing stress, we have here our formula 16 PR all over pi d cube. So the problem states that we will use the AM wall formula. So magiging 4m minus 1 all over 4m minus 4 plus 0.615 all over m, in which our m is equal to 2r all over d. So 2 The mean radius is 90 all over 20. So it is equal to 9. So substitute lang natin yung value ng m with 9. And then the rest of the given. So magiging 16. Our load is 1,500 Newton. Mean radius is 90 all over pi. The diameter is 20 raised to 3. And then 4 multiplied by 9 minus 1 all over 4. 9 minus 4 plus 0.615 all over 9. So the maximum shearing stress is equal to to 99.87 Newton per square millimeter or 99.87 megapascal. So ito yung magiging maximum shearing stress. And then let us now proceed to the elongation, in which the elongation is equal to 64 multiplied by the load, then r raised to 3 multiplied by n all over gd raised to 4. So 64, our load is 1,500 Newton. Mean radius is 90 raised to 3. Number of turns is 20 all over. Yung G natin is 83,000 megapascal. D raised to 4 or 20 raised to 4. So the elongation is now equal to to 105.4 millimeter. So this would be the elongation of the helical spring. So for number 2, a helical spring is fabricated by wrapping wire 3/4 inches in diameter around a forming cylinder 8 inches in diameter. Compute the number of turns required to permit an elongation of 4 inches without exceeding a shearing stress of 18 kilopounds per square inches. So the shearing modulus is equal to 12 times 10 raised to 6 psi. So our given, we have the diameter of the wire, which is equal to 3/4 inch. And then the mean radius or the mean diameter is equal to 8 inches. We will determine the number of turns. If we have an elongation of 4 inches and the maximum shearing stress is equal to 18 times 10 raised to 3 pounds per inches squared. And yung shear modulus natin is equal to 12 times 10 raised to 6 pounds per inches squared. So we have here the formula 16 PR all over pi d cube multiplied by 1 plus d all over 4r. So why did I use this formula? Kasi hindi naman naka-state sa problem that we will use AM wall formula. So gagamitin lang natin yung AM wall formula if the problem will state na gamitin natin yon. So the maximum shearing stress is 18 times 10 raised to 3 is equal to 16. And then yung P natin, and then yung main radius is maging 4 inches kasi diameter yung given all over pi, and then the diameter of the coil is 3/4 inch raised to 3 multiplied by 1 plus 3/4 all over 4 of 4. Yeah. So our P is equal to, so solving the value of P, So using your calculator or further simplify this formula. So our P is equal to 356.07 pounds. And we are now ready to determine the number of turns by using the elongation formula, in which maging 64 PR raised to 3 multiplied by N all over G D raised to 4. So deformation is equal to 4 inches. So yung deformation natin is equal to 4 inches. So substitute lang natin, 4 inches is equal to 64. Yung P natin is equal to 356.07. Mean radius is equal to 4 inches raised to 3 multiplied by N all over yung G natin is 12 times 10 raised to 6. Yung D is 3/4 raised to 4. So N is equal to, so isolate lang natin yung N and solving now for the value of N. So using your calculator, N is equal to 10.41 turns, or let's say 11 turns. Kasi wala namang 10.41 turns. So we have 11 turns. So this would be the final answer. For the next example, 2 steel springs arranged in series as shown supports a load P. The upper spring has 12 turns of 25 mm diameter wire on a mean radius of 100 mm. The lower spring consists of 10 turns of 20 mm diameter wire on a mean radius of 75 mm. If the maximum shearing stress in either spring must not exceed 200 megapascal, compute the maximum value of P and the total elongation of the assembly. So we will use AM wall formula, and the shear modulus is equal to 83 gigapascal. Compute the equivalent spring constant, which is the K, by dividing the load by the total elongation. So we have two kinds of spring here, or two sets of spring. We have spring 1 and spring 2. So our formula, we will use AM wall. So for the spring 1, so spring 1 muna tayo. So for spring 1, shearing stress is equal to 16 PR all over pi d cube. And then yung wall formula, or the wall constant, so 4m minus 4 plus 0.615 all over m. So computing first yung value ng m natin. Oh no, it is already given in the problem pala. So we have here m, the values of m. So ang gagawin lang natin is to substitute the values. So the maximum shearing stress of either spring is 200 megapascal or 200 newton per square millimeter. So it is equal to 16. Our P, R is 100 all over pi, D natin is 25 raised to 3 multiplied by 4, and then yung M natin is equal to 8. So 8 minus 1 all over 4, 8 minus 4, 4, 8. 4 multiplied by 8 minus 4 plus 0.615 ng ating M. So 8. So our P is equal to, so solve muna natin tong part na to. And then multiply natin by 100 by 16, and then divide by natin by pi. Multiplied by 25 raised to 3. And then 200 divided by yung makukuha natin dito. na product. So, our P. So, solve nyo na lang. Simplify and then solve. So, P is equal to, so our P is equal to 5,182.29 Newton. And then for spring 1, or spring 2 rather, so for spring 2, let's say we have shear 2. So, same din. Ito rin yung gagamitin nating formula. Kaso iba lang yung given. Since ibang set na naman ng spring. So, we have 200 is equal to 16 P. Yung R natin, and this part is 75 all over pi 20 cube multiplied by 4, and then yung M natin would be 7.5 minus 1 all over 4, 7.5 minus 4 plus 0.615 all over 7.5. So, ganun din. Kunin muna natin yung product ng factor. Kunin muna natin yung product ng mga ito. And then, 200 divided by the product para makuha natin yung value ng P. So, kaya nang mag-simplify. So, P is equal to 3,498.29. So, 3,498.29 Newton. So, we have two values of P, but we will consider the lighter one. So, our P is equal to, therefore, yung gagamitin natin P is equal to 3,498.29 Newton. So, this is the safest load that the helical spring can carry to be able to have a maximum shearing stress of 200 megapascal. So, ito yung magiging value ng ating P. So, this is the maximum value of P. And then, also, the problem is looking for the spring constant K. And makadedetermine lang natin yung spring constant K if we will solve the elongation of the spring. So, for the elongation is elongation of the spring 1 plus the elongation of the spring 2. So, yung deformation natin is 64 PR raised to 3 multiplied by the number of turns divided by GD raised to 4. For the deformation of the spring 1, so 64, P natin is 3,498.29 Newton. Yung R natin is 100 raised to 3, number of turns 12, all over G natin is 83 gigapascal or 83,000 megapascal. D is 25 raised to 4. So, the deformation 1 is equal to 82.87 millimeter. And then for the deformation 2, magiging 64, and then yung P natin (3,498.29). R is 75 raised to 3 multiplied by the number of turns, which is only 10. 10 lang yung turns ng ating spring 2. Divided by 83,000 multiplied by 20 raised to 4. So, the deformation of our spring 2 is equal to 1 71.12 millimeters. Therefore, the total deformation of the helical spring is equal to the deformation of the spring 1 plus the deformation of the spring 2. So, 82.87 millimeters plus 71.12 millimeters is equal to 153.99 millimeters. So, ito yung hinahanap ng ating problem. Then, the problem is also requiring to compute the equivalent spring constant. So, ito yung K. By dividing the load by the total elongation, so yung nakuha nating P kanina is equal to 3,498.29 Newton all over the elongation, which is 153.99 millimeter. So, the spring constant is equal to 22.71 or 22.72 Newton per millimeter. So, ito yung spring constant K. Next example. As shown, a homogeneous 50 kg rigid block is suspended by the 3 springs whose lower ends were originally at the same level. Each steel spring has 24 turns of 10 mm diameter on a mean diameter of 100 mm, and the shear modulus is equal to 83 gigapascal. The bronze spring has 48 turns of 20 mm diameter on a mean diameter of 150 mm, and the shear modulus is equal to 42 gigapascal. Compute the maximum shearing stress in each spring. So for the steel, the number of turns is equal to 24, and so dito na lang ako mag-drawing 24. The diameter is 10 mm, and then it has a mean diameter of 100 mm, and then yung G is equal to 83 gigapascal. So that is for steel. And then for bronze, N is equal to 48, D is 20 mm, and then the mean diameter is equal to 150 mm. G is equal to 42 gigapascal. We will compute the maximum shearing stress in each spring. So, drawing the free body diagram of this illustration, magiging ganito yan. So, we have the 50 kilogram, in which yung weight niya is 50 multiplied by 9.81. So, the weight of the bar is equal to 490.5 Newton. 490.5 Newton. So, this is in meter per second squared, and this one is in kilogram. And then we have here, let's say, the force exerted by the steel one, and then force from the steel 2, and then from the bronze. We have here, let's say, PB. This is 1 meter, so this is 0.5, and this is 2 meters. So taking the forces vertical, so taking the summation of forces vertical is equal to 0. So magiging PS1 plus PS2 plus PB is equal to 490.5 Newton. So this will be our equation number 1. So what else? Using the elongation, so magiging free body diagram ng bar would be look like this one. So this is the original position ng ating bar, diba? So let's say this is the original position ng ating bar, and magkakaroon ng elongation ng ating helical spring from the steel 1, from steel 2, and from the steel 3. So this would be the original orientation ng ating rod. And pag magkakaroon ng deformation from the helical spring 1, 2, and 3, the deformation will look like this. So this would be the deformation from the steel 1. This is the deformation from the steel 2. And then ito yung deformation ng ating bronze. So this is equal to 1 meter, then 0.5 meters, and then 2 meters. So by ratio and proportion, the deformation of the second spring, so this is S2, minus the deformation of the spring 1 equal to 1 meter. And then at this part, so this is deformation of the bronze minus deformation of the spring 1 for the steel, all over 3 meters. So continue po at this part, so magiging 3 the deformation of steel 2, magiging 3 multiplied by the deformation of the steel 2 minus 3 deformation of steel 1, deformation of bronze minus the deformation of steel 1. So simplify natin. So magiging 3 deformation of steel 2 minus 2 deformation of steel 1 is equal to the deformation of the bronze, in which yung deformation natin is equal to 64 PR raised to 3 multiplied by N divided by G D raised to 4. So substitute natin on this part. So lagay ko dito. So magiging 3 64 of PS2 multiplied by R. Yung R natin is 50. So multiplied by 50 raised to 3. The number of turns is 24. All over GD raised to 4. So G is 83 times 10 raised to 3. The diameter is 10 raised to 4. So 2 of 64, the load coming from the steel 1, so PS1 multiplied by 50 raised to 3 multiplied by 24 all over 83 times 10 raised to 3, 10 raised to 4. It is equal to the deformation of the bronze. So 64 PB. The mean radius is 75 raised to 3 multiplied by number of turns, which is 48, all over 42 gigapascal, 10 raised to 3, and then multiplied by the diameter, which is 20 raised to 4. So simplify pa natin further. So, 3 times. So, this part magiging 0.694 PS2 minus 0.463 PS1 is equal to 0.193 PB. PB is equal to 3.596 PS2 minus 2.4 of PS1. So, ito na yung may equation 2 natin. So, yung simplified. So, PB is equal to 3.596 PS2 minus 2.41 of 2.4 of PS1. So what else? So we can take the summation of moment of forces in point 1. So taking the summation of moment, we will take the moment of the forces at point, let's say point S1 is equal to 0. So magiging negative PS2 multiplied by 1 meter plus 490.5 Newton. Moment arm is 1.5 minus PB of 3 meters is equal to 0. So, simplify pa natin. So, magiging PS2 plus 3 PB is equal to 735.75. So, ito na yung magiging equation 3 natin. So, we have 3 unknowns, we have 3 equations, therefore, we are now ready to determine the values of each of forces. So, let us substitute the value of PB at this point. So, using equation 1 and 2. So actually, we can use our calculator in solving that. So if we will use our calculator, let's go to mode 5, 2. And then, i-rewrite lang natin in terms of sa pagkasunod-sunod. So equation 1, this equation 1, PS1 plus PS2 plus PB is equal to 490.5. And then sa equation 2, PS1 natin, so magiging negative 2.4 PS1 plus 3.596 of PS2 minus PB is equal to 0. And then for equation number 3, at this 1, PS1 natin is 0. So 0 yung PS1 and then PS2. So PS2 plus 3PB is equal to 735.75. So using your calculator, go to mode 5, 2, and then i-enter lang natin yung value ng 1. So 1 PS1 natin for equation 1 is 1, PS2 1, PB 1, and then 490.5. And then for equation number 2, PS1 is negative 2.4, PS2 is 3.596, then PB negative 1, and then 0. And then for the third equation, PS1 natin is 0, PS2 is 3.596, PB is 3, So, PS2 natin pala is 1. PB natin is 3. And then, 735.75. So, solving simultaneously, lalabas na dito yung mga values ng PS1, PS2, and PS3. Therefore, PS1 is equal to 144.71 Newton. PS2, 150.8 Newton. And then our PB is equal to 194.98 Newton. So these are the values ng ating P. And we are looking for the shearing stresses of each helical spring. So for the shearing stress ng ating spring 1, so it is equal to 16p r raised to 16p r all over pi d cube multiplied by 1 plus d all over 4r. So substitute lang natin. So 16, the p for the spring 1 is 144.71 Newton. Mean radius is 50 millimeters. All over pi, yung d niya is 10 raised to 3 multiplied by 1 plus 10 all over 4 of 50. So the shearing stress for spring 1 is equal to it is equal to 38.7. So the shearing stress 1 is equal to 38.7 megapascal. So this is our shear stress for spring number 1. For spring number 2, so 16, yung P natin is 150.8, and then 50 all over pi 10 raised to 3 multiplied by 1 plus 10 all over 4 times 50. So the shearing stress for spring 2 is equal to 40.32 megapascal. So 40.32 megapascal. So ito yung shearing stress ng ating spring number 2. And then for the bronze, so 16, P natin is 194.98. Mean radius is equal to 75. And then the diameter is 20 raised to 3 multiplied by 1 plus 20 all over 4 times 75. So the shearing stress for the bronze is equal to it is equal to 9.93 megapascal. So these are the answer for this question. The shearing stress for spring number 1 is 38.7, for spring number 2 40.32 megapascal, and for the bronze it is equal to 9.93 megapascal.